Hello, thank you for joining me. Welcome to episode one, series one of building an electric car. A while back, I actually designed an electric car for my son and I built it for him. It had everything from generator braking to solar charging. And I hope I'll be able to squeeze all of this into one series, but we'll see how it goes. Today, I'm going to talk about a buck converter. Now, bear in mind, I do expect you to have theoretical knowledge of what a buck converter is. Most of this series will be based on simulation and practical implementation, although I will touch on the basics slightly, but you should already be up to speed. So, what is a buck converter? A buck converter is essentially a circuit that converts a higher DC voltage into a lower one. That's all it is. But on a practical landscape, we would like to keep this output voltage as constant as possible, right? So the performance merits that I use to look at the performance of a buck converter are the output voltage ripple. Like I said, we'd like to keep that as constant as possible. The current ripple, the power output, efficiency, and there may be other performance merits depending on your individual design. Right. So a buck converter looks something like this. There are many other topologies, but this is one of the simplest topologies that you can implement. And basically we have our voltage source here and our output voltage through this load. This could be a battery or any other source that you have, a DC source. Okay. So in order to understand the implementation, or rather the operation, we'll have to consider two scenarios, that switch open with the switch closed. And the reason I'm going through this theoretical bit is so that you understand where we get the equations to select components from. Not that I'm actually teaching you how these operate. I expect you to have knowledge of how that is done already. Nonetheless, if we close the switch in the first iteration, what actually happens is the source will supply, or a current will start flowing from this source towards the circuit. But this diode is essentially a reverse bias because this node is more positive than the ground node. So this is reverse bias and it's essentially an open circuit. Well, there might be leakage current flowing through there, but it's in the microamp range, and who cares about that? Right. So if we write a KVL for the circuit in the outer loop, then VL would just be VS minus VO. And that's what I've written over here, where LDIdt is your inductance voltage, right? Now, before we move on over to this bit that might be confusing, because a lot of people will have the question of how did you go from a differential equation to just using deltas like this? Well, I want to answer that. And mathematicians, stay put. This is a physical world, it's not abstract. If we look at these quantities over here, Vs is a constant because the input voltage is ideally constant. The VO is also constant. We want to keep that output voltage as constant as possible, like I said. L is inductance. That's also constant. If we were to integrate I with respect to T, that would actually mean we're just integrating a constant. Oh, what's the integral of a constant? Oh, I know. The integral of a constant is just a straight line whose gradient is the change in y over the change in x, meaning it's a straight line of constant gradient. And based on that assumption, I can then substitute di over dt using delta I and delta t. Now, what do these mean? Let's sort of move away from the abstract world of mathematics and bring it closer to the physical world. Well, di, or rather delta I, is the change in current, how the current changes. So it's actually the ripple in the current. And dt is the time for which the switch is closed. Now, like I said, I expect you to be familiar with the fundamental concept. The time for which the switch is closed, what do we call that? Oh yeah, we call that the duty cycle. So this delta is actually our duty cycle, right? And the time for which the switch is closed is a duty cycle times your period, times your switching period, because it'll be close to say 60% of that switching period or 50% of that switching period. So therefore we can rewrite this equation as this. Simple, right? Then let's look at it when the switch is open. When the switch is open, the switch is open. Remember your Lenz's law? This inductor was charged when the switch was closed. We charged that inductor and it stored charge. And now that the switch is open, it is now going to discharge through the load. And because this diode will now be forward biased, will essentially be forward biased. Why will it be forward biased? Because this side is more positive than this side. Forget this mistake that I made over here. This side is more positive. That side is less positive. So it's going to return through that inductor, rather through that diode path, making it forward biased back to the inductor. So we complete our circuit in that way. We'll come back to what the capacitor does in a minute. Right now, just consider this LR circuit. So how then do we write the KVL loop for this scenario when the switch is open? Well, that's simple. Since this is our source, the source is equal to this output voltage. What about the capacitor? Well, the capacitor is in parallel with this. So whatever drops across this capacitor is actually what drops across that resistor at steady state, at least. So we can rewrite that as this, right? Okay, why the negative sign? Well, remember, this side is now positive and that side is negative. So do the math. So we've got all of that, and we apply the same manipulation that we used over there, and we get, let me rewrite this as delta instead of T, instead of dt, be that. I think I might have knocked over my microphone. And there we go. So for the same reasons that we changed the di dt above, we'll do the same then over here as well. Then what about this? What about here? Well, we rewrite the equation, but instead of writing d, we write 1 minus d. Where did that come from? Well, I'll tell you where that came from. Remember, the switch is closed for a period of d, right? And maximum duty cycle is 1. So if we close that period, if we close this switch for say 0.8 or 80% of the duty cycle, that means it's only going to be open for 20% of the period, right? If we close it for 40% of the period, it's going to be open for 60% of the period. So the sum of these percentages will always be 100. Same here, the sum of these, the total duty cycle, I guess, so to speak, should be 1. So if we close this for D, then that means it will be open for 1 minus D. Obviously times T, because we need to get a finite amount of time. And that gives you your two equations that define your ripple, your inductor ripple. Now, how do we conceptualize this? How do we visualize this ripple in inductor and all of that in an actual circuit using actual waveforms? Well, got your back. Over here is the inductor current that we would expect to get. We see that it rises, like we said, when the switch is closed. This is when the switch is closed. Over here, it rises to a maximum value where it's fully charged. Then we open the switch. When we open the switch, it discharges through the load. Then we close the switch again, it rises linearly, discharges linearly, rises linearly, and that's how we get our ripple. So these two equations define the ripple. You can use either of them. I'm just going to use this one because it's a lot simpler, really. Right. I'm going to use this one as a design equation. Why is that important? Well, we want to see the inductance that'll give us a certain percentage ripple, or put in another manner, if we want 25% ripple, that is if our 25% of the load current, how do I explain this? If our load current is 1, and we can tolerate a maximum ripple of 0.25 amps, that's what we're going to substitute here in order to get L. That would give us 25% ripple. So this will then be our minimum inductance that will satisfy that ripple requirement. Right. You can actually use that equation as well. This one, you'll get the same answer. I just prefer using this one because it's a lot simpler. Right. Now let's go to the concept of continuous current mode. And before we go to the mathematical aspects of things, let's get an intuitive feeling or an intuitive understanding of what CCM is. Continuous current mode means your current may approach 0, but it never stays at 0. What that means is this waveform over here will always be above 0. It may approach 0. It might even be 0.0000001, this low point over here, but it doesn't stay at 0 for a finite amount of time, so to speak. So why would we want that? Why do we care how long it stays at 0? Well, picture this. Let's say this current stays at 0 for 0.3 seconds. That means for 0.3 seconds, we're actually starving our load, because essentially no current flows. Well, there's a capacitor, yes, but you'll find out later that that's not a very reliable source. And I'll explain to you in a bit, but yes. So we want this to stay above 0. So how do we know what inductance value we should use in order to keep this above 0? Well, let's go back to mathematics. Well, let's look at this I minimum. This is what we want to keep above 0, right? So let's make an assumption here, and let's say the total ripple, or rather, the load current IR is midway between I max and I min. So it's right in the middle, down the middle, right? That's going to make our mathematical manipulation a lot easier. So let's continue then to do the mathematical manipulation. If we write I min in terms of IR, well, I minimum is going to be this IR over here minus half of this ripple. Remember I said that this is halfway. So half of this ripple subtracted from IR will then give us this I minimum value. That's what I've written here. And I've chosen the open switch ripple because it's, like I said, it's easier and it's expressed in a manner that is understandable. So then I substitute the value that we derived over here in this equation, and I get an expression for IR. Obviously, this is just Ohm's law. IR is VO over R. And from this, we can manipulate this and get L, the minimum value of L, in order to keep our converter in continuous current mode. And that's what I've done over here. And I've written it as an inequality because I need you to understand that L can be greater than this. That's perfectly fine. But it can't be less, because if it goes less than the value that you get over here, then you'll be in DCM, or discontinuous current mode. And this equation, I've just changed this T to an F, where T is the period and F is the switching frequency. Remember your fundamental T equals 1 over F. That's what I've done over here. So now we have two design equations to measure inductance, or rather to calculate inductance. We have one that considers CCM, and we have one that considers the current ripple. So which one do we use? Right. You use both of them, and whichever one gives you the highest value of inductance, you take that value. Why do we take the highest? Well, let's assume that you use this one and you got 10 microhenry, and you use this one and you got say 15 microhenry. If you use the 10 microhenry, yes, you will be in CCM, but your current ripple will be a lot higher than the requirements. And so your converter won't meet the requirements. And the converse is true as well. Right. The other performance metrics that we spoke about was the output voltage. Now, what dictates this output voltage? The capacitor. Now, this is where all the fun begins. What does the capacitor do? Well, the capacitor also charges and discharges like the inductor. When the switch is closed, essentially, well, not all the time when the switch is closed, you'll find that out in a bit. The capacitor charges, and after a bit of time, this capacitor will start discharging through the load. So it'll essentially keep the load at the same voltage as the capacitor, because you can see these two are in parallel. So if the capacitor had charged to, say, the supply voltage, 12 volts or whatever, and then as the inductor discharges, the voltage across this load will want to drop, it'll want to decrease because you're getting less and less current flowing through it. So V equals IR. Since I is decreasing, the voltage across here will tend to decrease. That's where the capacitor comes in. Capacitor will attempt to maintain the load voltage at the same voltage as the capacitor, say 12 volts or 5 volts or whatever the case may be, right? That's what the capacitor does. So how do we calculate the capacitance we need in order to essentially keep this voltage where we want it to be, or to keep the voltage ripple within acceptable limits? Right. If you remember your 11th grade physical sciences, then this is going to be a breeze for you. Remember, the charge stored in a capacitor can be expressed as the product of the capacitor voltage times the capacitance itself. Rather, the supply voltage times the capacitance itself, because the capacitor voltage is actually a rating and it's something else. So if we go back to these waveforms and we see how the capacitor charges and discharges and charges and discharges and charges and discharges, or how the capacitor current flows, and we'll see that here, when the current is positive, this is where we're charging. Remember, Q equals IT. And when the current is negative, this is where we're actually discharging the capacitor. So we're discharging here, we're charging here. Discharge, charge, discharge, charge. And we want to model a way to determine the capacitance to keep the voltage ripple within acceptable limits. So this is our starting point. Let's just consider the period where the capacitor is charging. And one other assumption that we have to make is that the charge in this area is equal to the charge in this area. Because if it's not, that would mean then we are storing infinite energy in this capacitor, and it will keep rising and rising and rising and rising. And that goes against the first law of thermodynamics. Right. Back to electrical engineering. So we can express this charge stored in this capacitor using this equation, right? Then where the hell did this come from? Well, this is a triangle. This is triangular. So to calculate the area underneath the triangle, what's the formula? Oh, I know, it's half base times height. That's what I've done over here to get this. And then I'm not going to substitute the equations we got for IL for the ripple current up there, because we'll already know what ripple is acceptable. And we can just multiply that out and get this expression. Right. Now that we have this expression, remember this is an expression of Q that we got using the area underneath. And this is a physical expression of Q. So we can substitute this into this area, into this equation here for Q, which is what I've done, and make C the subject of the formula. And this is what we have over here. So this is the minimum capacitance that we require in order to maintain the ripple voltage at whatever acceptable margin that may be. So our only design equation for capacitance is this one, right? That's it for this lecture. In the next lecture, we'll actually go into MATLAB and simulate this converter that you've just designed using an actual converter with real requirements. So like and subscribe, and I'm gonna highlight you later.